I'll tell you what, we have been waiting all year long to use this thing called Pythagorean Theorem. And I know most of you already know it, but I've been holding you off saying we have to kind of prove it before we really know it. Well, today is that day, my friends. So first of all, I've heard from you guys that you already know this, and yeah, of course we can already use it. So let's just make sure. What is the Pythagorean Theorem? Oh, by the way, those of you in the classroom, I've got you set up on GoGuardian, so you'll be able to contact me if you have any questions or comments, or for example, if you would like to contribute an answer, you can just put it in the chat. So let me open that up now. There it is. So as that comes up, you guys can contribute answers to it directly if you want to do it in the chat a little bit more discreetly. What is the Pythagorean Theorem? Come on, you guys know this.
A squared plus B squared equals C squared.
Thank you. And I'm betting just about all of you have heard this. But I'd like to challenge you, because if it's truly a theorem, then in fact, it has to be conditional, right? It has to be an if-then, or something can be written as an if-then. A squared plus B squared equals C squared is the conclusion, but under what circumstances does it apply? It doesn't apply in all cases. Like if I took all the A's in your names and all the B's in your names and I squared them each and then added them together, would they add up to the C's in your names? No, that doesn't make any sense. It applies when we're talking about a right triangle specifically, and we need the legs to be labeled A and B so that they're summed together when squared, and that the hypotenuse is C. And if in fact that is the scenario that we're talking about, then yes, this will apply.
Aren't we taking notes on a printed out note sheet?
You will. So I'm proving the theorem first, and then you'll have an opportunity. I'll walk you through the actual note sheet itself. For now,
I don't need to write this.
you don't need to write this, correct?
Okay, cool.
But I want, anytime we're using a theorem, I want you to know that it's true, right? If somebody says, how come it's true? You say, well, Mr. Erlin said it was true. That's not going to go very far in the real world beyond my bubble. So how do we know it works? Well, we should prove it. And if we're going to prove it, then we should start with our hypothesis. In other words, I'm going to start with a right triangle labeled A, B, and C. And that's all I get to start with. Now, I'm going to draw another one. In other words, I'm going to copy and paste a second right triangle that's exactly congruent to this. So I'd like A, B, and C. I'm going to have to put a little rotation on it as well to make it fit the way I want to, making this a straight line. And then I'll do it again. A, B, C. And we'll do it one more time. A, B, C. Does everybody agree that I began with a right triangle, ABC, and I've slowly, methodically, logically worked my way from there to create this shape? Okay, well, so what? Well, I want to find the area of this shape. Any ideas of what I could do to find the area of this shape? Well, I guess there's two ways I could think about it. I could break it down into all the little parts, and are those all parts that I could find the area of? And then I could add them together. So in other words, I'm going to say that it's 4 times the area of these little triangles plus the area of this little center looking thing. Can we agree that if I added up all 5 of those parts, that would be the area of the whole shape? Okay, so how do I find the area of a triangle? They're a very quiet group today, aren't they, Will? 1/2 base times height, right? In this case, I could choose like B as the base and A as the height, or A as the base, B as the height. Doesn't really matter. My answer is still going to come out 1/2 A times B. So for my area, I'm going to take 4 times 1/2 AB plus, and how do I find the area of this central shape? Well, I guess we have to know what kind of shape it is. What shape is it? It's a circle, right? No? What shape is that center figure that I highlighted yellow? A square. Good.
Square.
Good. Well, in fact, do we know it's a square, or do we only know it's a rhombus so far? Because I see that it's got all 4 sides are C's, but in order for it to be a square, I'd also have to know that these are right angles. Agreed? Without that, it's just a rhombus. So I'm going to have to do a little more thought process. I know that this angle and this angle, I don't know what they are, but I'm going to call them X and Y. And because X, Y, and this 90-degree make up a triangle, I know that X plus Y plus 90 equals 180. So in other words, X plus Y equals 90. Anyone want to challenge that idea that whatever these 2 angles are, they're going to be complementary? And since I copied this triangle to make all these, or this one to make these, then those same angles exist in all these other versions of it as well. Which means that when I look at this angle here, it's a straight angle. And if these 2 add up to 90, then this has to be a 90-degree. So Nick and Ellery were both right. This is in fact a square. It's got 90-degree angles in all these places. And therefore, that means that I can find the area by just multiplying the 2 sides, or C squared. So we'll clean this up just a little bit. This makes 4 times 1/2 is 2AB plus C squared. And voila, we've found nothing. That's not the Pythagorean theorem. So, well, what if I found the area a different way? Just leave that alone for a second. I can treat this thing as a big square, can't I? Because they've got a side length that's the combination of A and B all the way around, and it's got right angles. So I can say that the big thing, the whole thing, is a square as well, and it's going to be base times height, or length times width, but they're going to be the same. They're both going to be A and A plus B. That's the area of the shape. So then I'll FOIL this, or distribute property. AB, another AB is going to make 2AB plus B squared. Okay, good. No, that didn't really help me either. Except that aren't both of these formulas areas of the exact same shape? So if they describe the area of the same shape, then these 2 expressions must be equal to each other. And if I subtract 2AB from both sides, what I'm left with is A squared plus B squared equals C squared, which is what I was trying to prove. I started with a right triangle labeled A, B, and C, and I slowly, methodically created something, found the area of it one way, the area of it another way, and set those equal, demonstrating that A squared plus B squared equals C squared. In days of old, maybe days of yore, I'm not sure, they used to actually require people to come up with a proof of the Pythagorean theorem themselves. There's actually a great website if you're ever curious about a bunch of different versions of it. It's called cutthenot.org. I think there are dashes there. Be careful if you go to cutthenot.com. I think it's a divorce website, so different thing. So this is the Pythagorean theorem, and now we get to use it because now we've proven it. So let's fill in our notes. This is what Eloise was asking about. This is what you guys will have access to. So the Pythagorean theorem is used to find missing sides of a right triangle. It only works on right triangles. And when we're looking at this, we're talking about A and B sides being called legs, and side C is called the hypotenuse. And the reason these are distinct is because there's a difference. When we set up the equation, it is the leg squared plus the leg squared equals the hypotenuse squared. It's A squared plus B squared equals C squared. And it matters which one is C, right? It's the one that's not touching the right angle, whereas A and B are both touching the right angles. So for example here, if I want to find what X is, I can say this is a right triangle. Therefore, it falls into the Pythagorean theorem type problems. I can say that 8 squared plus the other leg squared is equal to the hypotenuse squared. So 64 plus 169 is equal to X squared, which means 233 is equal to X squared. But I'm looking for X, so that means X equals the square root of 233. Could I simplify that using the tools we've learned about? Maybe, but in this case, it specifically says round each answer to the nearest tenth. So I'm going to use a calculator instead. I'm going to plug this into a calculator, and it's going to give me that it's approximately equal to 15.264 something, something, something. And again, this asked me to round to the nearest tenth. So I'm going to make a little line after my first decimal pointed number, right? Here's the decimal. This is the tenths, hundredths, thousandths. And I want to decide if the stuff after this is bigger or smaller than halfway. 50 would be halfway between 0 and 100, effectively. So this is going to round up. I'm going to say that this is approximately equal to 15.3. That's now rounded nearest 10. I'm going to jump down here to number 3 next, because it's a slightly different application of it. Notice that now the X is in a different location. The X is now one of the legs. So when I set it up, I have to say X squared plus 7 squared equals 9 squared. The hypotenuse is over here. That has to be the standalone. So X squared plus 49 equals 81. Subtract 49 from both sides, and I get X squared equals 32, which means X equals square root of 32. And again, I could simplify by that. That comes out to 4 root 2, I believe. But this is asking me to use a decimal approximation. And this one's going to come out to 5.6569. I'm only interested in the nearest tenth. This is more than halfway. It's more than 500, so I'm going to round up. Any questions on this so far? Would you please do numbers 2 and 4 yourselves now? Let's get you doing a little practice. All right. So this time when we do it, we get 34.828. I draw the little line after the tenths, and this time it's only 28 out of 100. So that's less than halfway, so I don't round it up. All right, and then for this one, looks like it's a leg. So this is going to be part of the summed side rather than the solo side. And again, even though we're rounding to the nearest tenth, we don't want to be losing precision along the way. My number comes out to 364.81, and I'm not going to round that down now. I don't want to round until I get to the end. All right, any questions on this? What's your confidence in using the Pythagorean theorem to find missing sides in a right triangle? 5, I can do this every time. With a calculator in my hand, this should be no problem. I'll even get the rounding right. 3, there might be little tweaks in it. I might round wrong, or I might put a piece in the wrong place, but generally I think I'm pretty solid with this. 1, no can do, dude. Let's see what we got here from the peanut gallery in classroom. Nice, thank you, Emily, for a response. Thank you, Joe, for a response. Thank you, Maddie, for a response. Great. Okay, so what about these next two, 5 and 6? They aren't really so much right triangles, so it's a little bit more challenging. Good, kids. But we need a right triangle. The only way we can use Pythagorean theorem is if we have a right triangle. So here's a right angle. And this is the side I'm looking for, which is part of it. So that makes sense. I know that this, because it's marked as equal to that, is also 24. But my question is, how big is that? This asks us to pull back some old information. In an isosceles triangle, when you split it down the middle, if it's a right angle, it splits the angles, it splits the sides, it's an altitude, right? It has all those things that makes these two triangles congruent. So if this side is 22, that means this is 11 and this is 11. So now I've got the makings for a Pythagorean theorem. I can say x squared plus 11 squared equals 24 squared. So x squared plus 121 equals 576. X squared is equal to 455. So x is the square root of 455, which is approximately equal to 21.3307, which for our level of precision would be 21.3.
Do you have to take it out of the square root?
You mean rather than just leave it like this?
Yeah.
Yeah, that's an unfinished answer, and expressly in this particular series of questions, it said round your nearest answer, or your answer to the nearest tenth. So
How do I do that, the square root thing on my phone though? Because I don't have a calculator.
Is it an iPhone?
Yeah.
Okay, so you turn it sideways.
1
And you
second.
should get something like this. And then it's over here underneath the squared sign is the square root. And so you'd say, what do we have? 455, and then just press the square root button.
Oh, so I like, okay,
Do the number first, and then you say square root.
I see.
Okay.
Thank you.
Yep. All right, what about number 6 here? I mean, that's not even a triangle. How's that going to work? But we should be looking at the right angles, shouldn't we? We know those are going to do something for us. And in fact, if this is a right angle and this is a right angle, then that means that the side with 18 and the side with 5, they're parallel. Because these are same side interior angles that are supplementary, therefore it's parallel. So if I draw another one right there, and I force this to be a right angle, This one has to be a right angle. And I've now made myself a cute little rectangle. Because it's a rectangle, I know that if this is x, this is x. And if this is 5, this is 5. And if this whole thing was 18 and I've taken 5 off, that means this part is 13. And that now gives me the makings of a right triangle I can work with. So I can say that x squared plus 13 squared equals 16 squared. X squared plus 169 equals 256. X squared equals 87. So x is the square root of 87, which comes to 9.327, which around the nearest tenth would be 9.3. All right, I'd like you to circle number 7, please. That's going to be one of the problems for your homework. Any other questions on Pythagorean theorem? Finally, you guys get to actually use it after all these months of me saying, no, 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 you can't use it. Now, I have 2 kids, and you know that if you have any brothers and sisters, inevitably someone goes up to a parent and says, which kid do you like more? And I can truly say I don't have favorites as long as they know, or so much as they know. But I also know that, you know, there's this political thing. We're not supposed to have favorites in anything. Everyone's supposed to be created equal. Heck, our Constitution says it. But I got to tell you, there are some right triangles that are more special than others. So today we're going to talk about some special right triangles. And what makes them special is that we can actually find 2 missing sides given just one of them. Pythagorean theorem gave us the ability to find 1 missing side if we knew 2 in a right triangle. We had 1 missing side and 2 known sides. And we can do that all day long. But with these special right triangles, we can actually find 2 missing sides if we only know 1. So first, let's construct them or build them out of what we know already. I'm going to make an equilateral triangle. And you'll remember that that means all 3 sides are the same size, and all 3 angles are the same angle. Do you remember how much these angle measures are? Or could you figure it out? All 3 of them add up to 180. So 180 divided by 3 is 60. So all these angles are 60 degrees, but I'm going to do kind of like we did in that other problem. I'm going to drop an altitude. And when I drop an altitude, it both makes a right angle here, and it splits this angle. So instead of it being 60 degrees up there, it's now 30 degrees on each side. But I'm only going to look at 1/2 of this equilateral triangle now, because what I'm looking for is right triangles. And this is now a special right triangle. It's called a 30, 60, 90. In other words, it's named based on the angles that are in it. And what makes it special is that because it's half of an equilateral triangle, like let's say this side was, I don't know, 12. Then we know that this base down here with the altitude and angle bisector is also a median. It's going to split this in half, meaning this is 6 and this is 6. And then I could even find this missing side up here by saying that 6 squared plus the question mark squared is equal to 12 squared. 36 plus question mark squared is equal to 144. Question mark squared is equal to 108. So question mark is equal to square root of 108. Now, I could use a calculator and get a decimal equivalent, but that wouldn't show me much. That wouldn't help me. So instead, last class, we learned about simplifying radicals. I'm thinking that 6 goes into this because 6 goes into 10 once, 48, so it's 18 times. And then this is going to be 6 and 3. So in other words, I could rewrite this as 6 times 6 times 3. And if I want to rationalize that or simplify that radical, what do I write it as? Well, the 6 pairs up, don't they? Come on the outside, and I get 6 root 3. In other words, this height here is 6 root 3. Well, it turns out that based on what you guys have learned with your similar triangles, what if I have another triangle here that's also a 30, 60, 90 triangle? What do you know about this triangle and that triangle? They've got at least 2 angles the same. So they're similar by asimilarity. Beautiful. And as a result, we know that whatever the proportion is from here to here, like let's say this is 4, that means that I'm multiplying by 3 to get to 12. Or from 12 to 4, I'm dividing by 3. So if I want to go from 6, I'd divide by 3 again, and I'd get 2. And if I want to go from 6 root 3, I'd divide by 3, and I get 2 root 3. It turns out that the ratio of these triangles, sides to sides, are going to be the same as this every single time. So what this is going to give us, we're going to go to the second part here first, because I like the second part better. We're doing 30, 60, 90 triangles. And what we've just validated is that the side opposite 30, we'll call it A. Whenever that's just some value A, we know that the hypotenuse is twice that, right? Because it's half of an equilateral triangle. And so whatever this side is, when you multiply it by 2, that's going to tell you the hypotenuse. And if that's 2A and that's A, I could do the Pythagorean theorem all day long. And what I'd end up for this third side is A root 3 all day long. So this means that when I'm given a right triangle that is one of our special right triangles, a 30, 60, 90, if I'm told that this smallest side, the side opposite 30, remember our triangle inequality says that the side opposite the smallest angle is the smallest side, opposite the mediumest angle is the mediumest side, and opposite the largest angle is the largest side. So opposite 30 is 5. That means the hypotenuse will be double that, or 10. And the side opposite 60 is going to be that value multiplied by root 3, 5 root 3. What about number 5 here? Well, the side opposite 30 is 14. So that means our hypotenuse, the biggest one, is going to be double that, or 28. And the side opposite 60 degrees is going to be that 14 with the root 3 stuck on it. Oh no, they've changed it on us. They've given us the hypotenuse. Whatever shall I do? Any ideas?
Divide by 2 to get x.
Yeah, we know that this is twice as big as this part here. So if this is 32, x must be 16. And once we know that, this one is just that 16 times root 3. Same is true down here, right? It's the hypotenuse, it's the double one. So we'd say y is going to equal 46 over 2, which is 23. And then to get the one opposite 60, that's the hard one. That's just going to be 23 root 3. All right, jump to number 9 for a second. Some of you, I can hear your knees knocking from here. Right? You see that square root and you're like, oh no, it's going to be so hard. But this is the one that's supposed to be a root 3. So if that's 9 root 3, how big is x, the one we really want to work with?
9.
It's 9. So that when we multiply it by root 3, it becomes 9 root 3, which means then we double x to get the y. Y is 18. So easy peasy. Now, notice that so far we've been given Whole numbers as the one opposite 30, it's easy. Whole numbers as the one opposite 90, it's easy. A radical 3 opposite 60, it's easy. But what if they give us a whole number as the side that's supposed to have a root 3 on it? This is a little bit harder. In other words, I know that this thing is supposed to be a root 3. I got to find out what that a is because that's going to go down here. So I know that 20 is equal to the a root 3 I want. So then I just solve algebraically. I divide by root 3. So now I know that a is equal to 20 over root 3. And that is the number value, but we learned last class that when we work with radicals, we have to rationalize. We can't leave a radical in the denominator. So this becomes 20 root 3. 3 times 3 is 9. Root 9 is 3 again. So that's a pretty crazy looking number, 20 root 3 over 3. But that's the value here for y. 20 root 3 over 3. And then how do I get from there up to x? What do I do to whatever this y value is to get up to x? This case, it was times 2. This case, it was times 2. This case, it was times 2. So all we do is double this, which is going to make it 40 root 3 over 3. Doubling it is multiplying it by 2 over 1. The top gets doubled, the bottom does not. All right, what's your confidence in 30, 60, 90s? 5, I can do all of these really easily. 3, I think I can use the notes and do most of them. This part might throw me a curveball, but I think I can generally do it. 1, there's no way I can do this. It's got radicals on it. I love seeing the answers come in and go Guardians. Thank you. Emily, excellent. Caden's good. Joe, great. Maddie, good. Okay. All right. So now let's talk about the other special right triangle, because we said there's two, right? One of them is a 30, 60, 90s. And now the other one is a 45, 45, 90. And this one comes from a square. If I have a perfect square where all sides are the same and they're all right angles, then when I run a diagonal through it, I can create a right triangle where this is still 90. These have now been bisected, so they're 45 degrees. That's the name, 45, 45, 90. And whatever length this side is, and whatever length this side is going to be the same, right? Because it's isosceles. And then this piece, if I have a squared plus a squared equals question mark squared, that gives me 2a squared equals question mark squared, which means the question mark is equal to the square root of 2a squared. Well, we learned last class that we can factor this and look for what comes out. And what we get is that that diagonal is going to be a root 2 every single time. So this is the top part of our notes here. It says that in a 45, 45 special right triangle, if the legs are a, then the hypotenuse is going to be a root 2. So here's an example. One side is 8. How big is x going to have to be? It's got to be isosceles, right? These two angles are the same, so these two sides are the same.
8.
So x is 8, good. And then this one down here is just going to be stick a root 2 on it, 8 root 2. This one's 25, y then has to be 25, and x has to be 25 root 2.
How did you get, oh, never mind.
Okay, just following the pattern, aren't we? This one's the harder one, right? Because this is supposed to be root 2. It's not. So I need to solve for it by dividing by root 2. And that gets me a equals 19 over root 2. I have to rationalize that, getting me 19 root 2 over 2. And again, I recognize that these numbers are intimidating. Heck, 19 by itself is intimidating. It's like one of those constants that messes with people. It's not even, it's not divisible, but it's a prime number. Any questions on applying special right triangles? Got a couple pages here to work with. And again, look to see if it's opposite an angle that's important, 30-degree angle. So if that's a 2, and the hypotenuse would be a 4, and the end side here would be 2 root 3. I would like you to work on finishing these 6 problems on this page. They're very straightforward. And then these problems on this page that are both straightforward and more complicated. I am going to put you into breakout groups. I know that some of you prefer to be in groups with just your buddies, but today I want you to work with whomever it is that you're assigned. It'll only be a couple of you, and if you want to work together, great. If you want to just do it independently and have the person there in case you have questions, that's fine too. If you want to both be in the same room and not talk to each other and raise your hands if you have questions, you can do that too. All righty then, welcome back. Thank you for engaging and seeing how it went. I'd like to hear from you how it went. 5, I found it really easy. I was able to utilize the notes and the practice problems, and I think I did really well on it. 3, there were a couple that threw me. There are some challenging ones in there, and I really didn't know how to go about them. 1, I had trouble spinning it around. I couldn't tie them together. There are definitely some hard ones in there. There's no doubt about it. I think 3s is a reasonable choice at this point. Miss Betterton, a student teacher, had a really interesting point that a lot of times people have a hard time spinning these things around. And so, for example, if we're looking at this one, and that's an easy one. Well, sometimes it makes sense to like spin it, like draw the triangle the way you want to see it. You're used to seeing 30, 60, 90. And so now in this case, that would be opposite the 60. So I'd put the 15 root 3 there. And maybe by seeing that, it's easier for you to say, okay, so I know what's down here has to be the 15 and this is going to be the 30 because that's my relationship. So consider redrawing the triangles to help you orient it. Any other particular questions? Oh yes, here's one. 21 through 24, sure. So in 21, that's off the page for you guys. I see that this side is 12 in a 30, 60, 90 triangle. That's my hypotenuse, so that's supposed to be double the side opposite 30. So this side would be 6, x is 6. Then this shared side here is going to be that 6 with a root 3 stuck on it. And because this is a 45, 45, 90 triangle, I know that the two sides are the same. It's isosceles. So this is 6 root 3. And then whatever goes here is going to be this times a root 2. So in this case, as we learned last class, when you have a radical with 2 terms, you can multiply those terms and get 6 root 6. For number 22, if 7 root 3 is your starting point, that's your side opposite 30, you multiply it times 7 root 3 times root 3, which is 7 root 9, which is 7 times 3 is 21. So this side is 21. And then that's the starting point for this 30, 60, 90 triangle. So over here, this would be 21 root 3, and this would be 42. Okay, if you'd like to take off and do these on your own, or you want to go off and just do something else, great. If you'd like to stay, I'll go through 23 and 24 now as well. Have a good day. I'll see you guys on Thursday.
Thank you.
You're welcome. So let's see. What we're given is the hypotenuse of a 45, 45, 90 triangle. When that's 15 root 2, that means this is 15. And so is this. So z is 15. Ooh, the hard one. If this part is 15, it's not supposed to just be a clean number like that. It's supposed to be whatever this y is times root 3. So to solve for y, I'm going to divide by root 3. Those cancel, and I get y is equal to 15 over root 3. But that's not rationalized. This is what we learned about last class. That becomes 15 root 3. Root 3 times root 3 is root 9, which is 3. And actually that can reduce. That's going to be 5 root 3. So this side is 5 root 3. So that when it multiplies by root 3, it makes 15. Yes, this is 5 root 3. And then x is double that. So double 5 root 3 is 10 root 3. Okay, the person who asked me for these problems, is that helping? Or am I just doing it for you? Yes, that's helping. Okay, do you want me to leave you the last one and then I'll correct it? Why don't you guys try to do the last one yourselves? And then I'll give you the answer in just a moment. Hard to write, it's a 6 root 6. Okay, guys, do the best you can with these things. Some of them get more difficult, but make sure you can do the simple ones. That's the real key. If you don't have that, you can't possibly do the more complicated ones. Have a great day. I'll see you guys on Thursday.
Thank you.
Thank you.